Okay, so for the dot product, so there's also it's also known as the inner product or also the scalar product. The inner product term it's more like a linear algebra term as opposed to vector calculus type of term, but it's also used as well. And scalar product we call it because the result of performing the dot product between two vectors outputs a scalar as opposed to, as we will see later in 13.4 of the cross product, the output will be another vector. So that's why we will call it also the vector product. All right, so let's see. So let's have a look at two definitions. Number one definition involves trigonometry. So it's the product of the magnitudes of the given vectors times the angle in between the two vectors. So that's one version to calculate the to obtain the dot product. And the second way to get it is all we do is multiply the x components of the vectors plus the y components of the two vectors. And well, this can be extended, of course, to three dimensions, to vectors in space. So multiply the x's from the two vectors plus the product of the y's on the two vectors and the product of the z components of the two vectors. But again, the result is a scalar, not a vector. Well, why do we have two definitions? Well, we're going to use the first definition later to find the angle in between two vectors. So now we will be talking about two vectors, not just one at a time. So like many products, like the multiplication of numbers, both vectors have some properties of the dot product. So if we consider three vectors, u, v, and w. So in the plane or in space, it doesn't matter. So the properties are going to hold true whether we're in the plane or in space. So, and let's consider another constant c. That's a scalar, that's not a vector. So, well, it turns out like in multiplication of numbers or integers, well, actually any number, not just integers, vectors via the dot product are commutative for the products. That means u dotted with v is the same as v dotted with u. The associative property, so if we multiply a vector times a constant and dot it with another vector, so we can take out the constant, do the dot product, and then multiply by that constant. Or have that constant multiply the second vector. Okay? And then we have the distributive property. By the way, there's a little typo here for property number 3. The quantity inside of the parentheses should read, let me cross it out. Well, let me actually, should be W, not U. W, okay? So, and it's a distributive property, the same distributive property we know from basic algebra. So, U dotted with V plus U dotted with W, right? The dot product between a vector and the zero vector is 0 in this case, all right? Well, this one isn't that hard to justify because if we have a vector, say u1, u1, u2, u1, u2, and dotted with the 0 vector. So u1 times 0 plus u2 times 0. All of this is going to be 0. Notice the result, it's the 0 number, not the 0 vector. And you can see that on the notes. So notice how this 0 right here, it's a bold case as opposed to this 0, which is just a regular number 0. Of course, how do we represent that on paper? Well, you're not going to bold case the paper. You may tear the paper. So that's why we usually use the number with an arrow at the top to denote that it is a 0 vector. Right? Another very important property is the dot product of a vector with itself. It's simply its magnitude squared. All right? So, hey, what happened here? So, how about we look at some examples to see this in action. So, we're given two vectors, u equals 3, negative 4, 1, 5, and negative 2, 6. Let's find each of the following. Okay, so, u dotted with v. That is, So that is the vector 3, negative 4, dotted with 1, comma 5. What are we going to do? Well, x's with x's, the product of the x's, that is 3 times 1, plus negative 4 times 5. So, well, this is very simple arithmetic, I guess. That equals 3 in the first term, plus, or rather minus, 20, and this will be negative 17. All right? Okay, now let's do part B. V dotted with itself. V dot V, that is, it's going to be the vector 1, 5, dotted with itself. What is this going to be? Okay, so this will be 1 times 1 plus 5 times 5. All right, so that's 1 plus 25, which equals to 26. How is this the square of the magnitude of the vector? Well, how about we verify the fifth property with this example? Well, this 1 times 1 is the same as saying essentially, what's that? 1 squared plus 5 squared. All right. Also, I mean, if you want to simply take the magnitude of v, take the magnitude, that is the square root of 1 squared plus 5 squared. That's the same, right? That's equals to square root of 26. But what did we get? Didn't we get the square of this number? So that verifies that for that fifth property of the dot product. All right. Okay. Let's see. Let's have a look at letter C. So for letter C, what do we have? U plus V, that is the vector 3, negative 4, plus V, which is 1, 5. And we're going to dot this with, what's that? Negative 2, 6, right? So we're going to do like PEMDAS, in a way PEMDAS works. I mean, if you want to distribute the vector W, you will have to do 2 dot products, which is nothing too crazy anyway. But I mean, we can reduce the amount of work by doing the addition of the 2 vectors inside of the parentheses. So what are we going to get here? So 3 plus 1 equals to 4, and negative 4 plus 5 equals to 1, dotted with negative 2, 6. All right. So let's see. That's 4 times negative 2 plus 1 times 6. That's going to give us negative 8 plus 6, which is negative 2, which is, I saw some of you got this one, right? All of you, I think. Okay, so what about letter D, right? Alright, so for this one, feel free to use the word you already have from other parts. For instance, notice for the first part of part D, it's asking us for the dot product between U and V, but you already have that, right? So you can simply use it. And that'll be, okay, so that's negative 17. That multiplies the vector W, that is negative 2 times 6. And simply just multiply both numbers by 17 rather. That's positive 34 on the one hand and negative 102. All right. So that's just essentially it's a multiplication of a vector by a scalar. Now check this out. What about what about this one? So very similar. U dotted with V dotted with W. Right? What about this one? Looks very similar, but there's a slight difference that changes the whole game here. Yes. Yes.
I mean, it looks similar, but it's still another dot product, so it's just going to be another scalar.
It's going to be another scalar. Okay. Okay, let's have a look at it. Any other ideas?
Magnitude? The magnitude of the vector?
The magnitude of the vector. the magnitude. Any other ideas? Yes.
Maybe you could like distribute the W as like a dot product for with U and with Z.
Well, that we already did with the addition in between, but this is a dot, not an addition, right? So what about it then?
Well, like no, like you do a dot product between W and U, and then W and V, and then those two products you dot them together.
Okay, I see what you mean. Like, okay, 3 times 5 times 7, for instance, right? So you mean 3 times 7 times 5 times 7, something like this?
Yeah.
Yeah, well, I mean, but it doesn't work. Notice there's 2 factors of 7, right? So, all right. Any other ideas? Okay, what is this? Again, isn't that 17 from part A? Or negative 17? Yes, negative 17. Dotted with a vector. Okay, that is negative 2, comma 6. Can we dot a number with a vector? Not in this case, so that's why in this case, undefined. So all we can do in this case is dot two vectors in 2 dimensions. I mean, a vector in 2 dimensions with another vector in 2 dimensions, or a vector in 3 dimensions with another vector in 3 dimensions, or a vector in n dimensions with another vector in n dimensions. But if the dimensions do not match, this is a 2-dimensional, this is a 1-dimensional. In this case, it's not going to be defined. Okay, so with the first definition of the dot product, the one that involves the product of the magnitudes and the cosine in between them, of the angle in between them, we're going to solve this formula for the angle to find the angle in between 2 vectors. All right, so and it's actually the angle in between their standard position vectors. And well, a little bit of what's it called, vocabulary. Well, so when 2 vectors meet at a right angle, their dot product will be 0. You'll see that in the exercises here. And when 2 vectors have a dot product that is 0, there it is also say that the 2 vectors are orthogonal or normal to one another. So we're going to talk about this orthogonality of the vectors later in the next section. We're going to use it a lot. And when 2 vectors are parallel, either the angle in between them is 0 or 180 degrees. They're still parallel despite whether they go in the same direction or in the opposite direction. So let's find the angle in between the 2 vectors here, rounded to the nearest degree. Okay, the nearest 100th of a degree, that is to 2 decimal places. Okay, so let me give the formula here. So what do we need to get the angle between 2 vectors? Number 1, the formula right here calls for the dot product in between the 2 given vectors. And secondly, it's calling for the magnitudes of the 2 given vectors, which we're going to calculate separately and simply put everything together in the formula. All right. So, okay, let's find the magnitudes of the vector. I'm going to find the dot product. So U dotted with V. So don't forget the arrow at the top to indicate these are vectors. So that's 5, negative 3, 2, 1. So this will give us 5 times 2, that equals to 10, negative, that's 3 times 1, equals to 3, that equals to 7. So that's the dot product. So now let's find the magnitude between the 2 vectors. Okay, so the magnitude of each vector, that is the square root of 5 squared plus negative 3 squared. And that's going to leave us with the square root of 34. And the magnitude of V, same, 2 squared plus 1 squared, that equals the square root of 5. Okay? So what do we do now? Okay, let's put this all this in the formula. So theta equals to the arc cosine or the cosine inverse, either way, either notation you want. That is u dotted with v divided by the product of the magnitudes. So that is cosine inverse of the dot product, which is 7, divided by the product of the magnitudes, which is the square root of 34, times the square root of 5. Okay, so this is a very formulaic calculator. Just be careful with your calculator when make sure it's set in the correct mode. Make sure it's in degree mode. Okay, so let me see mode. Okay, it's in degree. Second quit. So I'm going to do second arc, so a second cosine. So what we got, 7 over, okay, be careful when multiplying these radicals right here again, because that's the square root of, okay, second square root of 34 times the square root of 5. And close parentheses. I made a mistake on purpose here. All right. So number one, I'm going to get an error domain, and that's because, well, this root of 5 here, it's actually multiplying with the 7, giving us a number that is larger than 1, which is out of the domain of the inverse cosine function. So to fix this issue, if it works for you, so it would be better instead to, okay, let me delete the radical as well, and multiply the 34 times 5 inside of the parentheses. That is, use the product rule for radicals and put it inside of one single radical, and that's going to give you the result, 57.5228. So round it to 2 decimal places, 0.53. Right? So the angle is approximately 57.53 degrees. Okay? All right, so for part B, 2 vectors. Now these are vectors in space. They have 3 components. So, well, let's do the dot product first. That is 1, 5, negative 3, and negative 2, 4, 6. Okay, so that is 1 times negative 2, that's negative 2. 5 times 4, 4 is 20, and 6 times negative 3, that's negative 18. All right? So the result of the dot product, that equals to 0. Okay, so that tells us the result. You don't have to find the magnitudes of the vectors or use the formula, because when the dot product between 2 vectors equals to 0, what does that mean?
Anything dividing by will be 0.
Oh no, I mean when the dot product of the vectors is 0, what does that tell us?
Cosine or inverse cosine of 0 will be 90.
Will be 90 degrees, and in geometric terms, they're orthogonal, and orthogonality means 90 degrees. All right, so no need to find to use the formula, find the magnitude. That's all you need. So my advice: every time you're asked to find the angle between 2 vectors, always do the dot product. If you get a number, well, that means you will have to go the extra mile, find the magnitudes of the vectors, and use the formula. Otherwise, the minute you get a 0, you're done. That means they're orthogonal, so the angle in between them is 90 degrees. All right, number 3 in the notes is it's about projections and vector components. Well, so in the previous couple of sections, we have been combined 2 or more vectors to obtain a resultant vector, a new vector. Now we're going to do the reverse. So we are going to look at a vector and we will break it up into 2 components. You know, it's one that we call the orthogonal component, and then we're going to use this to find what we call a projection. But what is a projection anyway? Well, a diagram will help us here. So suppose Suppose we have a vector here, a vector, let's call that vector u, all right? And then let's consider another vector here, that's going to be vector v, okay? So a projection, the projection, well, actually we can project one vector onto the other in different orders. For instance, this time I would like to project vector u onto v. So suppose, so we have the sun right here, right, at noon, right? What's that gonna happen? Well, that's gonna make the vector u cast a shadow here. Let's call that vector w. All right. So this vector, let's call it for now. Let's call it the shadow vector. Let's call it the shadow. Well, we will get into the more formal name for this vector, right? And well, let's call this w1 because in the end we will break this vector u into two components, not just w1, but also let's call this w2. Again, this is what we did in the earlier section. So we had a vector with two components, or adding vector w1 plus vector w2. What are we doing here? Aren't we really using the triangle method to add these two vectors? But this time we're breaking up that vector u into its components, right? So let's do a little bit of trick here because we want to find this vector w1. That's what we want for now. Well, we will later find that vector w2 for another situation, but for now we care about w1. So this vector w1 in terms of its length, so the length in terms of trigonometry, so this length of vector w1 is the adjacent over the hypotenuse. That means it's going to be the cosine function relating those two sides. Okay, so that'll be vector w1, the magnitude of w1. That's the length, not the vector itself. It's the length divided by the magnitude of the vector u. All right. So that's how we will get the length. We will use this relation later because I will derive the formula for the projection which you have at the bottom of the page, right? So we're gonna be using basic algebra and basic trigonometry to get this. Okay. So we're going to combine this trigonometric relation between the length of the shadow w1 and the given vector and the dot product to find, number one, the components of this vector w1 as well as its magnitude or its length. Okay, so to define this, let w1 be the projection of the vector u onto v. Notice the notation. This vector here u, it's the vector we're projecting, and the subscript v, it's the vector we're projecting onto that first vector, right? Okay, so this w1 is k times v over its magnitude. Well, what does that mean, and where did I get this formula from? Well, so this vector v has a magnitude, whatever it is, maybe 17, 59, 81, whatever that magnitude of that vector is. Okay, so we don't know. So, and this this vector w1, notice how it's just a portion, a fraction of that vector w. Could be half of it, could be maybe twice its size, maybe, well, at least for this picture, it's about half of it, okay? But how do we know what portion of it is going to be? Well, number one, again, we need to define a unit vector v that goes in the direction of v. How do we get that unit vector? By dividing a vector by its magnitude, right? So that's how we get a unit vector. And then if we want to obtain a vector in the same direction, that is 3 units bigger or 1/2 smaller, well, just multiply that vector by k, all right? And that's going to be this vector that is in yellow here, All right? And well, of course, for the sake of simplicity, for the derivation, let's think of this k as a positive number. Okay? Because otherwise it may get complicated. We may have to look at two different cases. Just one case is more than enough. All right. So what do we have so far? Number one, so we found the length of this vector using this cosine theta, the formulation we got before. The magnitude of W1 divided by the magnitude of U. Okay, and we also known from the dot product that cosine theta equals to the dot product between the vectors over the magnitude, or the product of the magnitudes, right? So I'm going to combine those two relations. So essentially we're going to do like a proof or derivation, the typical statement that says if A equals to B and B equals to C, then this implies that A equals to C, essentially, right? So that's the reasoning behind the derivation of this formula. So here, if cosine equals this expression and cosine is also equal to that expression, how about we put these two together? That is W1, the magnitude of W1 over the magnitude of U, equals the dot product between U and V over the product of the magnitudes. Alright, so notice how some terms just go away, like the magnitude of U. So in the end, we're not going to need the magnitude of U, and that's going to leave us with the following. So that'll leave us with simply the magnitude of W, which is the dot product between the two vectors, divided by simply the magnitude of vector V, which is the vector onto the first vector it's being projected, right? Okay. And well, what is this? Actually, this happens to be K, our constant K. All right, we'll see that later. So here, again, let's go back to the projection. Projection of U onto V. That's the vector W1. All right, that's a vector W1 right here. Okay. How do we define that W1? Okay, W1, again, we define it over here. So that'll be K times V over its magnitude. But what is K? K is this, what we call the scalar projection, that is the magnitude of the shadow, or the length of the size of the shadow, if you will. All right, so that's the size of the shadow. So this will be, let's just replace this, U dotted with V over, over magnitude times vector V divided by the magnitude of V again. Okay, so this magnitude gets squared. So that is U dotted with V over the magnitude of V quantity squared times the vector V, which is the formula we have right here. All right? So that's how we get this this projection by combining a couple of expressions and by defining the length of that shadow right here, right? How many of you are math majors, by the way? 1, 2, 3, 4. Okay, so there's a bunch of you. Okay, 4. It's a bunch. Yep. There's not too many of us. Yeah. Yeah, no, the reason I ask is because I like doing these derivations, and in past semesters I haven't had too many math majors, but that's I do this specially for you, the math majors. But I think engineering majors, chemistry majors, all of you I think you would like these derivations to see where are these formulas coming from, rather than, hey, this is the new topic, here's the formula, let's compute, but where do they come from, what do they mean, how sometimes this formulations put together a lot of stuff, right? Later on we're going to do a few more derivations like this. Well, it's time to put this to have this what do you call this formula in action. Find given two vectors in space, u equals to 3, 5, negative 2, and v 0, 2, 4. Find the projection of u onto v, that is proj u subscript v, and the projection of v onto u, that is the projection the other way around. Also, they're asking us to find the scalar projection of v onto u, that is, what is the length of the shadow of v when projected onto u. All right, so what do we need anyway? So we need the magnitudes of the two vectors anyway. So I'm going, and the dot product. So let me find the dot product, and let me find those at the top of the page, because I know I'm not going to have enough space in right here. Okay, so the dot product, u dotted with v, that equals 3, 5, negative 2. And dotted with 0 to 4. 0 plus 10 plus 8. Minus 8, right? That equals to positive 2. So that's our dot product. And the magnitude of the vectors, the magnitude of u, that equals the square root of 3 squared plus 5 squared plus a negative 2 squared. And that's going to give me give us square root of 38. Magnitude of v, 0 squared plus 10 squared plus negative 8 squared. Okay? All right, that's going to give us 20. Notice in this case, I didn't do all the calculations inside. I think, well, at this point, you know how we get them, right? Okay. Let's see. So, find the projection of u. So, part A, find the projection of u onto v. Okay. I'll show you a little trick to memorize the formula, even though you're not required to memorize formulas. Yes?
For the magnitude of v, I think we did like the magnitude of like the sum of like, yeah, the dot product.
Of the dot product, did I? Ah, yes. But still I got it right somehow, right? By a mathematical miracle or something, right? Yeah, that's a one supposed to be, right? Yeah.
Is it v over u or u over?
Is u onto v, right? So here it's going to be the dot product over the magnitude of v squared times vector v. So in this case, a trick to memorize the formula, the subscript tells us what vectors go there. The dot product, it's always going to go the same in the numerator, so that doesn't change, right? But again, you're on the exam, you will not be required to memorize any formula. So let's see. So let's substitute. Okay, so whoops. U dotted with v, that equals to 2 divided by the magnitude squared. By the magnitude, which is square root of 20 squared, times the vector v, which is 0 to 4. Okay, so the square root of 20 squared, that cancels the radical with the squared. That's 2 over 20, 0, 2, and 4. Equals, okay, so 1 over 10, that's 1/10, 0, 2, 4, which is 0, 1/5, oops. 4 over 10, is that 2/5? 2/5. All right. So that's the vector. That's the projection of this vector, right? So that is, okay, so this is the shadow vector of u onto v. Okay? All right, let's see. Let's have a look at letter B. For letter B, the projection the other way around, the projection of V onto U. That's going to be, well, that's going to give us you'll see how that's going to give us a different result. So the dot product, which is 2 over the square root of 38 squared times the vector U in this case. 3, 5, negative 2. So again, the square root of 32 squared, that cancels the radical with the square. So that's 2 over 38 times the vector 3, 5, negative 2. 2 over 38, does that reduce to 1 over 19? And just multiply 1 over 19 with the three components. That is 3 over 19 5 over 19 and negative 2 over 19. All right. So do you see how the result is different regarding depending on the order of the projection, because they're not the same vectors. Unless we had the same vectors, well, that'll be weird. Actually, they're overlapping vectors, right? So, okay. Part C, the scalar projection of V onto U. That is, so for the scalar projection, that's simply this factor right here without multiplying by any vector. So in this case, well, the one quantity that goes in the denominator, okay, that's the scalar projection of V onto U. That's the dot product divided by the magnitude of the vector we're projecting onto, that is vector U. Let me highlight it so you can see which one is it in particular. Okay, so we got the dot product, which is 2 over the magnitude of U, which is root of 38. So that is the length of the shadow. That is the magnitude of this vector, if you will, right? All right. So how can we apply this to physical situations such as work and force? Okay, so in Calculus 2, most likely you did a few physical applications of integration, such as finding the work done by a variable force, where you just integrate some f of x from a to b, and then you had the spring case where you have to find the spring constant and the like. But also that construction came from finding the work done by a constant force before it became a variable force. So here is the thing. So how do we relate this to work and force? Because again, check this out. A diagram will help us again. So suppose we have this force vector, and okay, that's a force vector, and this is some distance vector. So we're going to find the work done by that force into moving a particle or an object from point A to B along some distance, say this vector d. Let me pause the recording for a little. Okay. So work force times distance, so we can also express it as a vector, the force vector dotted with the distance vector. That is, using the other definition, that will be simply the magnitude of the force times the magnitude of the distance times the angle in between the two vectors. That is my 45-degree angle I did with the table, for instance. Well, not 45, let me just call it theta, all right? So in terms of projections, so this will be, so the work, this vector W, that'll be the actual work, only a portion of the force of the big F vector onto the vector D, all right? The shadow of it, that's it. So vector W will be the projection of the force onto the distance. That is the dot product between the force and the distance divided by the square of the magnitude of the distance times the distance vector. All right. So let's have a look at one very simple example, very formulaic, very straightforward type of application problem. So what do we have? A toy wagon being pulled by exerting a force of 25 pounds on a handle that makes a 20-degree angle with the horizontal. Find the work done in pulling the wagon in 50 degrees. So if we didn't have the 20-degree angle, we simply multiply 25 times 50, force times distance. That's a very linear work. But that's not the case, unfortunately. So we're moving this force onto, we're applying this force at an angle of 20 degrees. So let's do a simple diagram. Force of distance, and there's a 20-degree angle. So let's just substitute the numbers. All right, substitute the numbers. That is the magnitude of the force. It's given. That is 25 pounds. The magnitude of the distance. That is our, 50 feet. And what's next? Let's just use the formula. Work equals force times distance. Force times distance, that is the magnitude of the force times the magnitude of the distance, cosine of the angle. So that is 25 times 50 cosine of 20 degrees. And using your calculator, you should get about 1174.6 feet-pound. All right, let's talk about the units for a second. Notice in this case we are talking about the force, but they're giving us pounds. Keep in mind that one thing to keep in mind is that pounds are units of force. Yes, they're also units of weight, but keep in mind that weight is it's force and mass is amount of a matter, right? So a way to trick you up about a problem like this is to give you, say, kilograms instead of pounds. If you were given units of mass, then you would need to find the force by multiplying by the acceleration constant by 9.81 meters per second squared, because we need to turn that mass into a force. All right. Mass is not, again, here's where we go back to the difference between scalars and vectors. Mass is not a vector. Mass is a scalar as opposed to weight, which is a vector. All right. So okay, so about parallel and normal forces. So how about we twist the diagram a little bit? So rather than having a horizontal distance with some force potentially in the same direction or at an angle, which in the end will be simply a projection at the full potential, how about instead we have an incline, okay? Let's call this vector V, okay? And instead we have some force pointing down, right? So again, we want to break up that big F force, that force vector. So again, how do we go from the tail to the head? Oh, I mean, of course, downwards. But in terms of components, we're gonna go like this, all right? So again, triangle method, if you will, but broken up into pieces. So let's call this W1 and let's call this W2. All right? And we're going to use this idea of the projection in order to solve those physical applications. That is, when you park a car or a motorcycle on an incline, what is the minimum force that in order to keep the car or the motorcycle from rolling down the hill, right? That's because, so that's going to be the weight of the motorcycle or the car or whatever it is. And in the end, that force is going to get projected onto the incline. So that's going to be simply the projection of F onto V, which is this vector W. All right. Again, this W1, it's the shadow vector of the force onto the incline. All right. So let's have a look at one example and wrap up the section. So we have a 200-pound motorcycle that is parked on a 10 degrees slope. And in this case, well, let's assume that the only force to overcome is that due to gravity. Because again, in your physics classes, you have that friction. Of course, that could be another vector adding here in the force diagram. But we're going to skip all that. But we only want to consider gravity. So they're asking us to find the force required to keep the motorcycle from rolling down the hill. Okay, so force diagram, vector diagram. So that'll be, okay. So this is V, okay. This is the force vector, that is the weight of the motorcycle, which we will represent as a vector soon. And this is the angle of 10 degrees. Well, that doesn't look like 10 degrees, but let's pretend it's 10 degrees. Okay? That looks more like 30 degrees or so. But I need the space for the diagram. Okay. The force is it's due to gravity. So if we were to represent the weight of the motorcycle as a vector, how would you represent it? Two components, by the way. That's my hint. Decompose it. So keep in mind that that the weight of the motorcycle is going down, right? Due to gravity. So how would we cosine and sine? I don't think we're gonna need sines and cosines here. Zero, okay, 0 for the x component. And what about the y component? Negative 200, right? Negative because it goes in the direction of gravity, right? So negative 200. But we have a little problem here. We don't know the vector that describes the incline. They're just telling us it's a 10 degree slope, but that's it. And actually, and it doesn't matter if the incline is 2 yards, for instance, or half a mile, or 1,000 miles. It doesn't matter really, because, and yes, the distance won't matter. You'll see that later. But because we don't know the components of those vectors, well, actually we can use that unit vector representation. Remember this? V, magnitude of V, cosine of the angle, sine of the angle. All right. So, so for the incline, that's what we have. And well, but hold on again. That magnitude of vector V, that should be the length of the incline, which we don't know what it is. Again, right? We don't know. And actually, we don't care. It could be 5, 73, a million. It doesn't matter. For the sake of simplicity, let that incline be 1 unit, maybe 1 meter. All right? Maybe 1 yard, or whatever the unit. Doesn't matter. So I'm going to represent then the incline using a unit vector. Let me change the notation here for unit. All right. Well, let me just go with the regular notation. That's fine. So that'll be cosine of 10 degrees, sine of 10 degrees. And well, so what do we need? We need the dot product of the force and the distance, that is the force vector, which is 0, negative 200, and the incline, that's cosine 10 degrees, sine of 10 degrees. Okay, 0 times the cosine, that's a 0, and minus 200 sine 10 degrees. Okay, So that's going to give us simply negative 200 sine of 10 degrees. Okay? So now we will find the projection of the force onto the incline. That's going to be the minimum force in order to keep the motorcycle from rolling down the hill, right? So that's going to be, well, the dot product between the force and the distance divided by the magnitude of the vector describing the incline squared times the vector that describes the incline. Okay, so we can do a few simplifications here, because the denominator, the magnitude of v squared. Well, what's the magnitude of v? What number did we choose for v? What is 1 squared? Simply 1, right? Again, if you want your incline to be 5 meters or a million meters, substitute a million here and then a million here and square it. You will see how those numbers are going to get canceled anyway. So that's why it doesn't matter what's the length of the incline anyway. So the dot product, which we already found, that's negative 200 sine 10 degrees over 1 squared dotted with the vector that describes the incline. Alright, so okay, let me make some space in here. Okay, cosine 10 degrees sine 10 degrees. So this will be in the end negative 34.73 times cosine of 10 degrees sine of 10 degrees. So doing all of this in the calculator, whatever cosine of 10 degrees is, make sure your calculator is in degree mode, times negative 34.73, that's going to give us negative 34.202, comma, whatever sine of 10 degrees is in degree mode, times negative 34.73, that's negative 6.03. Okay? And well, that's going to give us that's the vector projection, the shadow vector, if you will, right? W1. But we want to know we want to know this as a magnitude, right? So that's 1. Okay, so we want to find the magnitude W1. That's the square root of negative 34.202 squared plus negative 6.03 squared, and computing all this madness in the calculator, that should give you 34.7 pounds. Alright, so that's the minimum force to overcome in order to keep the motorcycle from rolling down the hill. Alright. Okay, so this finishes the section.